Well, I found out I was a complete idiot and forgot to record. So, I'm going to give a quick rundown of what's happened here. So, once you get your board with your footprint set up in your schematic and you go to your PCB, you're just going to have a giant mass of components. There's not going to be really any rhyme or reason to where they're placed. So, what I do first, what you should do first really, is separate them loosely into their subsystems. They should be close, and then after that, you're going to pass back through them and get them into their final footprint placements. So generally, you want to make it as tight as possible without causing signal issues. This is a pretty slow board, so I'm limited more by physical space than electrical signal spacing. So I basically have just gotten everything pretty much as tight as possible here. And I'm moving on to final components. So with these like dip chips, really any chips, you want to rotate them to where the circuits that each side is pointing to, that side of the chip is where all the signals that go to a subsystem circuit are. So like the signals that control this are here. The signal produced, the reset signal here is here, test pins are here, and then these light pins are here. And we got our programming header. Let me get that right there probably. So, I need to place this now. I put it there. No matter what, I'm going to have overlap with one of my photoresistors. So it's not going to be perfect. Actually, this needs to be on the bottom. Actually, no, this does need to be on top. What am I thinking? We got ground there. We'll do something like that, I think. Yeah. I'll have to route power, but whatever. How did I do it? Yeah, yep. Alright. That, get the designator out of the way. Put it there. That's good. Actually, I'm going to put this on the bottom side so it doesn't extend the board upward. Okay, that side's good. That. And it's going to be probably right about here. Approximately, I don't know yet. Could get that one really tight. This is for the bumper. Where are the bumper ones? I'm going to go back to the schematic here. So the bumper are actually on that side of the pick. The bumper ones are here, so that is going to influence me to place this more over here. Because this is through hole, I have a lot of wiggle room with routing. So actually, yeah, this is gonna come out pretty nicely. Pull this down. I'm gonna turn the rat's nest off for now. Move this up a little bit. And then I need to get, these resistors are, what are these? These are the pull-up resistors for the bumper, or the pull-down resistors. Okay. So I actually need to go look at this chip. Let me think. The sets are on that side. The sets are in fact on this side. So this one's positioned pretty good for what we want. And we have any grounds here? We got 5 volts. But we have grounds here, so that'll be good. So let's pull this maybe like this and just kind of stick it here. Get that inside. And we can move these out over a little bit. Alright, and then get this one. Okay. There you go. Then we got our bumper switches. These ones, ooh, yeah, that's a problem. I need to pull these out a little bit. Can't go too much though. That should be good. See you, Nick.
See ya.
Alright, we're about done here with component placement. So actually, I'm stupid because I can just put this here, and then I can put the other one right about here. I'm gonna get him to the edge of the board though. It's gonna be right about there. Alright. Now let's get this over. And we roughly have a board. Ooh, those are quite a bit higher actually. I'm gonna move these down. Hey. And let me get these on the edge. So there we roughly have our components placed. So I'm gonna come up here, I'm gonna put my thing right about here. And I'm gonna look at my grid, which is right down here. And that is about Y173. Actually, yeah, we'll do Y173. So I'm gonna make my grid size a lot bigger now, like 5 millimeters. And then I'm going to go down to the layer edge.cuts. This is our board outline layer. In KiCad, this will be different in others. And then I can come over here to draw a line. And, well, I'm going to do just that. I'm going to draw a line. But I want to get this done quick, so I'm just going to go big. So now I have a board outline, but a hard edge is never cool. So we're going to add some arcs. So to do this, I'm going to click here on this grid. I'm going to come up, and you always have to rotate clockwise with the arc. And that'll add a 5 millimeter radius arc. That's that. Come over here, do it here. Clockwise. Boom.
Now, why are you adding the rounded corners instead of keeping them pointy?
Partially aesthetics. Also, it won't poke you.
It's not racing to me.
Yeah. So after we have the arcs placed, we can delete our original lines. And we'll just be able to go to the edges of the arcs. Now, if you were doing a professional board, you would make the board as small as you could really fit it. I am going to change the component placements a little bit because this board is a little bit bigger than it has to be. And I can wiggle up some room. And I need to keep things away from the edge. Like this is... actually that's like 5 millimeters from the edge, is it?
How can you tell?
It's about 2, so I'm going to move everything up.
Are you using the dots?
You see here,
Indicator?
this is... If you look right here, you have your X and Y chords. Right,
Those are
yeah.
millimeters?
Yep, in millimeters. So it's 2.5 from the edge of the board, roughly, but you don't want it to be that close necessarily. I'm gonna kind of just move this up and over here. Maybe a little too much. Actually, my grids. Oh, my grid is 2.5 millimeters. That's why. I'm gonna change it down a little bit smaller. I don't want that. Don't want to move this up too much, but what I do want is this. Let me get this over and kind of up. Like, there we go, that's better. And then the same thing for this side. I need to get those caps in. I didn't move them the first go. Yep, so now I can move this one over. Whatever. It'll be manufacturable. I'm gonna get the grid a lot smaller. I'm gonna go back to 0.1 mil in meter. Mils are a thousandth of an inch. A lot of American corporations might use those.
Mils are what?
Mils, thous, thousandth of an inch.
Millimeter and a thousandth of an inch are just similar enough?
No, they're quite different actually.
Okay. I thought they were different. But I wasn't sure.
Yeah, we'll get that kind of nicely edge placed, and the other one's a little bit. We'll center it. There we go. All right. That's roughly going to be our final board placement. This is a great place to put a logo, which, if I have time, we'll go over. Alright. I have no gaps, whatever. Let's go back to the 3D viewer. So now it's going to update, and there's basically what our board is going to look like when we have it soldered up. Except these are going to be female. And also those. And that'll be a button. But I think the rounded corners looks a lot better.
Oh, that looks sweet.
Yeah, here.
That's so cool.
We'll get a logo on. So at this point, I'm ready to do board stack up. So
What about mounting points? Do you need mounting
that's
points?
actually a really good thought. Yeah, you probably want mounting points.
That's what I had to do for my job.
We could put one here. We can put one here, relatively easy, or maybe here. Actually, you know what? We can put one here. I can get a footprint in. Add footprint hole. Mounting hole 2.1 millimeters. Yeah, we'll get one here. We'll get one here. Kind of just hacking this in at the end, but it's fine. And a mounting hole there. Alright, let's go back to look at the 3D view. Now we have mounting holes. Very cool. Alright. I'm going to go ahead and make sure these ref stars don't get in silk screen. Properties. Front silk. Put it on fab. Ugh. And fab. Whatever, back fab, who cares? Alright, so at this point we're gonna go over to our manufacturer. We're gonna figure out what they can do and how we're gonna control our impedances, because in high-speed designs you absolutely need to control your impedances. So if we go to capabilities here, we can go to our controlled impedance PCB layer stack up. Most pins on chips are terminated in 50 ohms, and if you have impedance discontinuity, so if one has a characteristic impedance of like 100 ohms and then it immediately sees something larger or smaller, you'll get reflections and you'll lose power and it'll waste power. You'll learn about that in EMF. So we're going to go ahead and go with, I believe 2313 is my favorite, because 4-layer impedance, 1.6 millimeter. This is going to be important here, so I'm actually going to go ahead and move. I need to open board setup. And can I?
That you lose power because of refractions.
Reflections, yeah, and it can mess up in a signal integrity as well.
And what is that caused by?
The impedance changes.
Oh, between like.
So if you have one net, which is like a node, if you're taking ECA or more advanced circuits classes, at DC, it's effectively a short, but as you get higher and higher frequency, a thin wire becomes an inductor. And it also has an impedance, a characteristic impedance. So, like a coax cable would be like 50 ohms. Yeah, fields.
Yeah,
Transmission lines.
you just said that you get it from EMF.
So we're gonna take the actual information. Well, first we're gonna make this a 4-layer board, because just do it. Front mass 0.01 millimeter. That's generally fine. So this is kind of annoying to see because of my window manager. So our top copper is 0.035 millimeters, which is what we have. Our pre-preg is 0.1, which is this dielectric one here. And that's 0.1 millimeters, so that's a lot bigger. Golly. Oh, I clicked enter, so now it's gone.
Nice.
Yes, there's no good way to do this.
That sucks.
Well, I know this one, this dielectric here, is also going to be 0.1. The inner copper is, I did it again. Come on, me. So our inner copper is going to be 0.0175, and then there's going to be 1.265 in between them. 0.0175 is half of 0.035. That's half weight copper. 75. 0.0175.
You send in a PCB board schematic and it has like a different thickness than what they support. Are they going to just change it?
So the schematic, this is kind of just setting up for the calculator to make sure on your end all your impedance controlled traces are the correct impedance. And this also helps KiCad's internal routers for like a differential pair, like a USB signal or an HDMI or Ethernet twisted pair, to be properly impedance matched. So 1.5 there, and then it's 1.265 on there.
But when you send it into the
Mhm.
company, they can still do, even if you do.
So you'll tell them, they see the copper and the outline, and that's all they care. Okay, copper, outline, and joule. That's all they care about.
So,
Okay.
do they basically just follow the instructions you give them blindly, as long as it doesn't cause things to break?
Pretty much.
So it's up to you to make sure your
Alright,
product
so
performs how you want it.
we'll go ahead and click impedance controlled, and then I need to get the dielectric constants in.
What are the limits on that?
So if we go up here, our core dielectric constant is 4.6, and then our prepreg is 4.05. So coming in here, this is 4.6, and this one's 4.05, this one's 4.05. And then this is our solder mask. What's our solder mask? This is important for microstrip line. So solder mask is 3.8.
I don't know if it's like any of them.
So now we have that.
Wait, question. Would you guys like me to leave you pizza?
I'm good.
Have a second.
Alright, so that we have that done, we need to go change our design rules, which we can also look at the website. So we've got controlled capabilities. So our minimum trace width is going to be, where is it? Blah 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 blah. Drill hole size. So our minimum via diameter is, I believe it's going to be 0.45 millimeter diameter and then 0.2 millimeter hole size. So we'll go ahead and get that in. Minimum via through hole. Seaman. What am I looking for? Hole to hole clearance. Oh gosh, where is it? Hole tolerance. Clearance. Let's look at clearance real quick. So hole to hole clearance is 0.5 millimeter. We can get that in here. You want to make sure if you get your manufacturer's capabilities correctly input. Okay, that's different nets. Same nets, 0.254. Yeah, we'll leave it as 0.5. I don't think we're gonna have a big problem. So, leave, yeah, okay. Minimum clearance, minimum track width, 0.2 millimeters, that's about 6 mils. JLC, which is this Chinese one, they're pretty good. Trace width and spacing, here we go. 4 layers, 3.5 mil, 0.09 millimeter. 09, 9 millimeter. Okay, I did it again. Minimum annular width. Okay, so you have 0.25, 0.125. width. About that, we'll leave minimum clearance to 0 because we won't stupid. Copper to hole clearance. Let's go back down to clearance. Copper to hole. Here we go. Via to track. 0.254 millimeters, which is what we already had roughly.
Is this like what they recommend, or are these their limitations?
These are their limitations, basically. What they can consistently manufacture and not charge you an arm and a leg for. Okay, so that's roughly there. It's good enough at this point. You'd really want to go through. So the next thing is we need to calculate our 50 ohm track line. So JLC has a calculator. Somewhere around here. Here we go. JLC PCB impedance calculator. If you're on Windows, you can use something called Saturn. Outer layers. Impedance value. We're going to say 50 ohms. Calculate that. And then we chose JLC 2313 because that's the tighter stack up. It's 0.1 millimeter between copper layers, which is going to give you a lot better grounding. So our minimum track, our signal track size is going to be 5.78 mils. So we're going to come in here, we're going to add that. 5.78 mil, MIL, that's thousandths of an inch. So I'm also going to add a few more, like 15 mil, 30 mil, and like 50 mil. Those bigger ones are generally used for routing power. And then on our vias, we're gonna have one via. Actually, we'll do two. So our size is gonna be 0.45. So they can actually go down to 0.4 if you pay them more, and then the drill will be 0.2. And then I'm gonna add a bigger one. We'll do 2 millimeters with a 1 millimeter hole, and then we can use that for other things. And that's what we're going to do before we start routing. So let's start routing.
Yeah, this is the one part.
Yep. So we're going to leave, you always leave power last. Because generally going to have ground planes for ground, and then power is generally the least important signal. So one thing that's weird is at very high frequencies, well, at DC, a ground plane, you always want to leave a return path for your signal because you have a current going down, you also have a current coming back. And it needs to have a nice clean path because if you don't, it's just going to radiate EMI everywhere, and that's not good. You don't want that. That won't pass FCC. Actually, I need to make sure. These are signal traces.
That's interesting.
So, here we go. Here's our 5.78 mil. Oh, great. I'm going to have to come down this way, I think. And this one, I think I'm going to length match. I'm going to show you guys that tool. So, these are the programming wires. It's not going to affect capability, but I think it's good to show you. So, if you come up to route and then tune the length of a single track, I can look at what this one is. It is 32.171 millimeters long, and what's this one? 35.2495. So we're gonna tune for this one. 34. What is it again?
So you're making sure all your wires are the exact same length.
You don't have to. It's basically required for a double data rate memory interface. So let's see. Length tuning settings. I think it was like, we'll just go for 35. Actually 0.5. I remember that. And then click OK. So that one's now tuned. Let's go to this one. And that one's now tuned. So these are now same length, which means coming from here to here, it will take the same exact amount of time for the signal to propagate, because electricity is also a wave.
Oh, that's so cool.
And you're avoiding sharp corners, right?
For very, very high-speed signals, you would want to avoid sharp corners. Actually, that's another thing. I haven't messed with this yet. So, how do I do it?
Petercraft did a presentation on PCB.
I know KiCad added a tool recently for... Let's go ahead and get the easy ones. So, I think Shift X. No? Okay, maybe it's just X. What is it? Yeah, Shift X. No, it's not. Okay, whatever. Just gonna start routing things up. That doesn't really matter. These and go here, go here. Yeah, it's really low speed. Cool. Yeah, I'll do that later. Let's get the motor signals. Actually, I don't want to do the motor signals right now. You know what? I need to. I'm gonna plane that anyway. No, I don't have time for planes. We'll do 15 mils. This one is okay. That's apparently really small. Yep, through hole's huge. Okay, then we connect that there, that there. This, you can get really artistic with this.
They're bigger now because you have to worry about the motor. Right?
Yeah, you need to. Generally, you can, if you're in a really tight situation, you can calculate exactly how much current or how wide your trace needs to be to handle the amount of current that's going through it. We're not space constrained, so we don't necessarily need to do that. Ooh, that's fun. Oh, wait, there it is. I'm blind. We'll have to do that on the back. We'll go ahead and pull it through on the back.
Oh, that's.
Yeah, that's probably the best way to do it. This one I can do on top. Yeah, that's not gonna hurt anything. That one leaves that in a somewhat precarious position, especially if I have to take it down there. You know what, I'm gonna do it on the back. Really, I need to move this one up.
I love PCBs. They're so cool.
That there.
Oh, that's so cool.
I'm gonna get the rat's nest back. That just, will tell me what I'm missing quickly. Yep, this. Well, these are signal wires now, so these need to be small boys. Here we go. Wait, nope. And you know, I want to go front for now.
It's so far away.
Oh boy. I can get that on the bottom. Oh goodness, that is pretty far.
You can always do through holes too, right?
Yep.
I had to do that a couple times.
Got that. And let's get this one. Just gonna place it there to be a little more. What is it doing? Okay, you know, whatever. Not the most efficient trace, but who cares? Oh, that's a problem.
So the
To the
bigger
back.
lines for your power.
Or things that'll be higher current traces. I kind of generally just go by the as big as I can get, but you can't always do that.
So then you actually have to do the math.
Yeah. Math, you.
I like that approach better. Just make it bigger. It ought to be good enough.
There we go. Alright. Then we got this one. This is a lot wider than the surface mount board.
If it wasn't big enough.
Oh, you know, if I route it through there, I need to get these traces done over here before I do that one. Otherwise, I'm gonna be walking on thin ice. We knew MCLR. That one's cute. That's a ground. So this reset internal. Oof. And you know what? Let's just do it. Let's go to the top layer. This really isn't that important that you get this perfect. I want to go straight down. Right, not Q. Uh-oh. We can just go around the back. Again, you may have to do a lot of soul searching to figure out how to route denser boards. that? Oh yeah, this goes back to the pick. LRST. Yep, I can just go straight over like that.
I didn't know there was so much wiring.
Hmm?
I didn't know there was so much to this. So does it really matter, like, how long the wire is for high frequency?
Yes, it can matter a lot.
Damn.
Eventually, so you've probably learned at this point that a digital signal is the sum of a lot of cosines, right? So those cosines have extremely high frequencies. Like if you have 100 megahertz square wave, the harmonics that get you that nice edge can be up into the gigahertz. So you have to design for your circuits for this, your PCBs for the gigahertz, not the megahertz.
Wow.
And depending on your rise times, eventually it's going to move slow enough, or your trace is going to be long enough relative to the frequency of your circuitry that it becomes a transmission line rather than just a net. And then you have to model it completely differently. That's the field stuff. I'm a computer guy, so
Yay, that'll be
I'll leave that to the other guys. Got ground there. What's yelling? 5 volts. All right, this is pretty much routed there. Let's go ahead and do this. Ooh, okay, going a little too close to that mounting hole. And I want to leave space for an OC logo.
You can always draw on top of it.
Yeah, but I want a copper one because gold looks better. Hey, we got that. So now it's just power, power, power. Any signals? No signals. Oop, this one actually. Yeah, this is a signal. So this one's gonna come all the way up here. That's kind of disgusting. And I'm gonna have to route 5 volts to that eventually. Ew. Alright, so that's all the signals up there.
Connection, the lines disappear.
Yep.
So all the straight lines are the things you haven't done.
Exactly.
That's very useful. That would be hard to do.
So we need to take this on the back side of the board. This right motor positive. Flip back up to the fat trace. We might have to change these to be 30 mils, but hopefully not. There we go. Alright, and then right motor negative. That's going to be a problem. Because I have traces on 2 layers going there.
Oh no.
There, that's not cool. So maybe I can route around. I could go up and around. That's really long, and then it'll conflict with those signals. Well, actually, no, it won't. Yeah, I can drop that down to like a 15 mil. Or maybe even 30. Yeah, here we go. I'm going to try to stay away from that pad a little bit.
Oh, that's fine.
Did I hear you correctly that you're trying to avoid having to take that trace between multiple layers?
Yeah, I don't want to add a via, because that takes up a lot of board space. So by routing it around, sure, it makes the trace longer, but this is really, really slow, incredibly noisy analog circuitry, so it literally does not matter that the links are all off.
Because that's just the motor. That's just basically making sure the motor can turn on and off.
Yep.
Right?
That's just the connection to the motor, plus and minus.
Yeah, so
Yeah,
the
plus and
motor
minus
doesn't
is
care what
arbitrary.
signal it gets, does it? It's just
Nope.
sends a bunch of
This is 5 volt power. We'll go ahead and put a fat boy on it. Those are grounds. Okay, let's go ahead and start doing this one. I'm gonna pull up my other one to see if I have any useful insights. Yep, there's no useful insights. So, those are straightforward. I'm actually gonna, I want symmetry, so I'm gonna keep with the 50 mils.
Oh yeah.
Eek.
Yeah. Yeah, he did.
Alright, now this one I have to route on the top layer. This is the fun part. So what is this? L1G. Oh, I have to get that one all the way over there. I can do it on the bottom. Go around on the bottom.
Might be, so, wish me luck.
You probably don't need it if you think such a cool.
So Josh, when did you make that decision?
I made that decision myself.
Yeah, but when?
Oh, when?
Yeah.
Before I came here.
Okay. I see you already like had a lot of computer stuff,
So is that root?
or at least
almost
gaming.
I
You
see
already
the
had your
left
interest in
root around.
computers. So that's just making sure it's meeting clearance. So you see the kind of gray
Mhm.
past the blue. That's like the minimum clearance we had set earlier.
Oh, that's cool.
Yeah. So there we go. That's connected up. Grounds. We don't care about that.
Ground.
Okay, this one.
Let the rest of each plane.
Yeah,
right?
basically. Well, the two inner ones are basically, they're likely going to be purely ground. I might have to write power on one, I don't really know. Yeah, I can take that on the back.
Oh boy.
And then the other one I can get on the top.
Yeah. Wait, is that a different color?
So this
Oh crap, I just put that on the middle layer. That's not smart. I don't like that. That doesn't look cool.
So the benefit of placing your parts closer together is you have to pay less for a board because it's smaller. But the downside is it makes it a lot more difficult to route.
I might pull up, I might show you some stuff I've done in the past that's fun.
I'd imagine.
Incredibly dense.
Yeah. That's
For what?
I'd imagine they have routing software.
Yeah, it sucks. Don't do it.
That is a whole problem to solve.
Yeah, it really is. Alright, so ground, that needs to go to the pick.
like
Power.
steroids.
And pretty much everything's routed
Sound.
except power. We're about done here.
Computer. Computer.
So let's go back to our signal size.
Oh, I heard putty.
Oh.
Putters. Yeah.
Yeah.
Yeah,
Where you
yeah.
have to like find the least like path or whatever.
Yeah, ours. So, like, I had my putter dialed in perfect the night before the competition. I came in, Dr. Bigwell was in the lab, and I tuned it a bunch. And then
There we go.
it was matching
Power.
perfectly.
Power.
And then the day of competition, nothing worked.
Power. Okay, we have not connected to
The
this.
person who did the best accidentally grabbed the wrong person's putter. They won. They had their calibrated for their putter, and they grabbed the wrong putter the first time. Better.
Where's RQ?
So they used that. I think they're still trying to figure out the inconsistencies in the putters.
Do I have an RQ? That's kind of scary. Yeah, I think we do. Oh gosh, here it is. That's pretty scary. Oh, I did not get an RQ on the schematic. That's bad.
RQ being,
Yep, I named it LQ. I'm retarded.
okay, that's an naming thing.
Yep, and now I've already routed that, so
When you change
I have to rip up
trace
trace.
on the schematic.
When I have to come up to this and then click update PCB. So now it's going to tell me that I've connected left Q here. Yep, I used to be able to backspace, I missed that. So now I have the right thing, and it looks like I can cleanly get that on the back.
Oh, you are? Yeah. Oh, sweet. Yeah.
Except I have to go around because
Much better things for you to spend your time doing. They've already made that. That is pretty good.
yep, RDPilot's pretty good.
Yeah.
I really want to go now.
Wow. It depends on if we can do a good enough job. And I'm pretty sure the answer is no. It is
Good.
something else.
That's the right answer.
The engineering projects are nebulous. In fact, it is impossible. You could not design a flow controller for under $200. Especially they can do chemical control. Chemical control pool systems are within the
Alright, I think every single one of our signals are routed at this point. We might have to rip some up to get power. But I'm gonna go ahead and get the ground planes in, so
Literal crash course. You will crash.
next step is getting a polygon. So to do this, we're gonna need to change our grid size. And then let's come for a polygon fill. And I should, so this is gonna be ground. Our signal return paths, we're gonna get ground, and then just drop this clearance to like 0.2, otherwise it won't be very friendly. This is through hole, so probably still want to add thermal reliefs.
Some people that you're really quick. You know, time management, you don't manage your time. You won't do it. You won't produce a good result.
Type solid fill, and then we're gonna go ahead and up this zone priority a bit. Click OK, come up here.
That's good. Faster.
But my friends are just doing so much faster.
I'm pretty slow, I think. But that could be that I'm ridiculous. So what's this you're doing here, Zach?
I am now adding a ground plane to
Okay.
the inner layers of the board. So this is going to be used as the signal return path for pretty much everything. And as you can see, none of it actually came in, so I have to double click on it. Or
So what is the ground plane? Like physically?
It's just a sheet of metal. And
Yep.
it's tied to ground.
Is this for the relays?
there you go. So now I have ground planes on
Oh.
3 and 4. And if you remember from earlier, I mentioned that every signal needs a return path. That's what these are. So now every ground has been routed. And oh, that's a problem. I missed that. That's a signal trace. Eek. Route. Okay, so now we can see what we've missed. So obviously we don't have any power routed. And that's going to be a bit of a pain. Especially since there's so many signals just going across the board in a mess. So let's go ahead and do this. Let's get 5 volts. 5 volts is pretty quick. That's connected there. Come up across. Get it here. And then just a little bit more here. What? My computer is, it's reaching its limits.
Oh no.
So is it not letting you route the trace?
No, it's the suggested routing is kind of getting bogged down. Oh, that's a problem. To the back. These are really big polygons, and the way these things work is it's basically a giant text file.
Wow.
Wait, a text file?
Yeah.
Oh, and now you have G code.
Yeah. That's a good point. CAD is a lot of that.
That, okay, that's a text file.
So we need 5 volts there, we need it here.
Something interesting. If you're using HTML, all your web pages have to go to 7-bit ASCII and back. So you have to figure out how to convert things like video into ASCII.
Wow.
There's a problem.
They designed HTML in the early days of the internet, and it wasn't used for entertainment, it was used for research.
If it's
So,
It was originally designed, it was the government used that.
both of those can go over. So you know what, I think I'm going to rip these up.
That to talk and share their research. So when they developed the protocol, the 7-bit ASCII made perfect sense. Why would you need the 7 bits? Just use ASCII, there's nothing else.
yeah.
Shit, I need to drop my grid size a lot.
Yeah, we're like deep. The amount of shoehorning that's been done to get the internet to work is ridiculous.
Yeah.
Everything was built where we could trust everybody.
That's right.
And then this one.
There's some technologies like
Oh, way older than that.
Ethernet is ancient in terms of networking. But they were able to just keep updating the protocol and keep making it faster. So it's still viable today.
Alright, I think that's pretty much all the power. Oh, wait, no, I'm blind. 5 volts, 5 volts. And I can take that on the bottom. We.
Now everything's full duplex. Switch to duplex, which is basically, think of it as a highway. So you don't ever go into
I can get that on the bottom. Let's go.
There's a lane for sending, there's a lane for receiving, and they never cross. No signal should ever come into contact with another signal.
There, I can get that on the top. I can get that on the top. I can get that on the top too. Boom, boom, boom. Yeah?
You created the ground plane, but that doesn't necessarily connect to like all of the pins, right? All the 3 poles.
Yeah, it does.
Oh, it does.
Because when it fills it, it'll see if it's the same net, and if it is, it'll just. Here, actually, let me turn them on. And then we get the opacity up.
Oh, so it's
See where they're ground?
Oh,
Yep.
that's cool.
Yep.
Okay. Okay, that makes sense.
Yep.
Thank you.
No problem. Alright, I think I have a couple more power signals over here. I can get all of this on the top layer. Sweet. That's not the top layer. That's bad time. Okay, and then we have this. Oh,
Oh.
well, actually, I don't know why that's glitching out. That's connected. That's really funny. It's connected. It'll get. We'll go over it in DRC here, which will happen in like. Actually, I think it's time to get an OC logo on this.
Alright. This is the part we were all waiting for. Although I was probably waiting for us.
We'll
to
run
put
DRC
in
real quick.
A picture that says,
Is this
plug
it?
power in here.
So if we come up here, this is the design rule checker. This just is going to run through our design and see if there's any violations. It's going to reflow everything. Silk screen overlap.
Which means,
Not cool. So I'm going to move these a little bit.
so that meant your letters were overlapping.
Yep, so we're going to go to this one. That one's fine now. Okay, there were 2 there. No, that's not what I want. This. Here we go. Let's go here. Error footprint. What about it? What are you saying there, DRC? Courtyards overlap. I don't really care about any of those. So they're all courtyard overlaps and then silkscreen overlaps. Q10, Q10, Q6. Let's get this one. Yep, I don't like that. That's bad. So actually, let's put it here. Oh wait, that's for this one. There we go. Cool. And then the rest are just courtyard overlaps. That's not a big deal. Unless, actually, so that can be a big deal when you're working with really tiny stuff. There's this thing called the tombstone effect. This is more related to big ground planes. So a big sheet of metal, you can call it a ground plane, but it's also a heat sink. So if you have one end of, say, like a tiny little 0.5 millimeter long, 1/4 millimeter wide resistor connected, fully shorted, no. So there's things called thermal spokes. So instead of just fully filling around the pad, it'll just put little tiny spokes to it, like a wheel. You have chalk? No. Dang it.
There's one whiteboard
Here, I
all
can
the way over by
pull up
Josh.
GIMP.
Whiteboard marker all the way over by Josh.
We'll just pull up GIMP. We'll get it on the video.
Yeah,
New,
that works.
whatever. Black. Okay, we're gonna write in white. So let's get a pen. So say I have a pad here. Blah blah blah. This is my beautiful art skills. So you're gonna put a resistor here.
I'll have to put up with mouse art.
Right, there you go. So This side is connected to something. Let's say this maybe like trace about this big,
Oh, it's
right?
Yeah.
But this side is just fully connected to like a giant ground plane. And just imagine this is a huge heat sink. So what will happen is when you do reflow soldering, this solder just won't, the solder paste on this pad will not melt. And it'll pop up and it'll be vertical on this pad.
Oh, yeah.
Here, I'll just,
That's not good. Yep.
there you go.
So that is a component that's now upright that shouldn't be.
And that won't work.
Well, no, I would imagine it won't.
Might not fry anything, but it won't work. There's some more examples. See, that trace is fat.
How big is that?
That's probably 0402.
Which is a grain of rice?
1 millimeter long by 0.5 millimeter wide. That's as small as I've hand soldered. It takes forever.
So tombstone effect is that only for really tiny things?
For the most part. But you definitely need to be wary of it.
Is
Because
there a way to combat it?
yes, so is there a way I can actually let's just Google thermal spokes KiCad. That might get it.
Oh,
Here we
so
go.
you-
Yeah. So instead of just shorting all of that and just having full copper, it reduces the size of the copper connecting to that pad, which means it has a higher thermal resistivity. Because, well, it's smaller. There's less metal to go through. Okay, what do we have left? I think we just passed design rule checks. Let's get our OC logo. This is a fun part. So somewhere, actually, you know what? Let's just go and get an OC logo. There we go. That's when I searched it when I was doing it. Not that OC logo. Here we go. So let's.
The real logo.
Yes, the real logo. We'll go ahead and save this image. Oh no, you just saw my system stuff. Yep, it was a failure. Just don't do systems, guys.
Just don't do systems.
If we don't do systems, we have to be a CS. You can't graduate without systems.
Save. Why does it keep trying to go in there? That's annoying. KiCad logos. You know what? We're just gonna save it in here. All right, cool. So KiCad has this. Do I have the main thing open? No, I don't. All right. I'm gonna get this moved over. Go 5. So if you come down here, where is it? Image converter. This one's fun. I'm gonna send this one to 6. Oh, alt not. Alright, so we're gonna load our bitmap image. I guess I already had it. We'll just go from here. So we have an OC logo.
Okay.
We have a black-white threshold, and that red's sort of dark. But I'm gonna up it a bit. Wait, crap. This isn't gonna work very well. Because we have this white out here. So
The white to transparent.
here we go. You know what? I think that's fine, and then we can make it negative. Ooh, okay, that didn't look too good. Ooh, no, I think we need to work on this. So let's pull it up in GIMP. Good little free photo editor. Doesn't use you. You use the software. It doesn't use you. Let's open our OC logo. So this tool is the fuzzy select tool in GIMP. So look, I just clicked and it selected all the values that were within 15 integer counts between that. And now I'm just going to, what do I want to do? I want to make that dark because I want the OC to be the cat. Yep, okay. So let's make this black and we're going to bucket fill it. Then we'll fuzzy select this inside the O.
You missed a little bit at the bottom as well.
Yep, good catch. Oh, yeah? Yeah. I've used GIMP for probably a decade. So at this point, now we can fuzzy select the other stuff and actually.
Yeah, it took forever. It's so simple too.
dropping this threshold. Eventually we'll find the right one that'll just auto select everything because I'm a stickler and I want it to look clean. Perfect. So you also have to worry about silkscreen thickness because there are minimum values that they can make with silkscreen as well. Did I just select everything? Crap. I think I did. There we go, that's good. Actually, that probably should be black, but you know what, actually, I think we're done with this. That's gonna look pretty good. So let's go ahead and overwrite that. Go back to KiCad. We're gonna load a different bitmap. Oh, is that the one I just got? I think so. No, where did I put it? I'll have to go back to the internet browser. Downloads. Where did I send it? OC_shield.jpg. File, actually, let's export as OC_shield. Black, white. There we go. Export. So now we can go back to KiCad. I know it's here. And here we go, it's this one. So now we can tune it. That looks pretty sharp. So over here we can now set how big it is. I think 5 by 5. Oh wait, this is gonna go to solder mask. Solder mask is negative, so the O will be open, I think. Yeah, that's what we want. We want it as a KiCad footprint, and let's go back to our board and see how much space we have. So Control-Shift-M to measure, and we can roughly fit it here, but we don't want to put our names on it. Looks like we can get about 8 by 8. Yeah, let's do that. 8. There we go. Then export it. Some footprints. OC logo _8 by 8. And we're going to save that. Now we're going to go back to our board. We can go to place footprint. Gotta load the footprints up. And we should just be able to search an OC logo up. Voila. So we can go back to our 3D viewer. It's currently only on the front solder, pulling the front solder mask. Now what we're going to do is we're going to duplicate it. Right, and then we're going to right click, and then we're going to go open in footprint editor. And I can select everything, or I'm going to right click this, I'm going to go to properties, and we're going to put it on the front copper. Properties, copper. Properties. I could just press E and not say properties 4 times, but I'm lazy. And then we're going to close that, and then we're going to save the changes, which is going to put this one on the front copper. So now we can move that right on that, and then get rid of these G++s. No one likes those. Delete. No, I didn't. Properties, we can send it to fab instead of deleting it. It's probably the best thing to do. Fab won't get, well, fabricated. You could choose and make it fabricated. Now let's look at it. That's not what I wanted to look at. Now it's gold. We might move it down a little bit. Kind of get it centered in there. Footprint G. Alright, there we go. Let's go look how that looks. Yeah, it looks a bit better. Now it's time to put our names on it. So let's just go down here to text. Fundamentals Robot Revision A. Revision A is 4 of 22, April 22. And this is OC IEEE's robot. I'll put this on the mask so we don't have to do that later. And then we're going to center it. And we might have to lower the thickness a bit depending on how big it is. Yeah, we're going to have to make it smaller. So let's make it 0.75. Click OK. Yeah, that's better. Now, let's go ahead and get this centered. It's getting a little close there. We can move the logo to the right a bit if we need to. And then let's duplicate this and put this on the copper. Now we got our names on it. There you go. Fundamentals Robot Rave 422 OC IEEE. You can put more on there if you want.
So Zach, why do you put a silk on and then the copper?
Because gold looks a heck of a lot better than white.
But why do you have to put the silk on first?
So it's not actually silk, it's the solder mask. I'm saying don't put solder mask here, so it reveals the copper. There's actually some circuit art with, there's a manufacturer called Osh Park, Osh being open source hardware. Yeah, yeah. So they have this one thing called After Dark, and it's a black fiberglass substrate and then clear solder mask. And then so you have, I guess you have solder mask over substrate, that's one color. No solder mask over substrate. Copper, no solder mask. Solder mask on copper, and then silk. So you have like 6 or 7 colors, and you can do some pretty cool stuff with it. So that's pretty much our board at this point. It's pretty wide. I don't actually know how big it is. It'll fit. It's probably about the size of. It's a little bit. It's gonna be maybe half an inch longer and 3/4 of an inch taller than a small breadboard. We can measure it real quick. Control Shift. And it's roughly 90 by. This is actually going to be kind of expensive if we were to buy it by 60. Yeah, it's kind of expensive. But at this point, the board's done. This is a lot. Actually, you know what is. It's connected. We'll go ahead and make sure it's. Hey, I'm running trace, right? Yeah, here. Boom. I don't know why it's not happy, but it isn't. Or have I? Yeah, I connected it there. You know what? That actually isn't connected down here. That would have been terrible. So, how should we go about this? I could take it on the top and then down and around. I could just connect this on the bottom through here. It's probably the best bet. Alright, so now those are all our traces routed. We can save it. Alright, we're about ready to go get these files out. So our PCB is done. Let's go take a look at it real quick. Good. You know, the back's a little bare, but whatever. I don't really want to add more logos. I want to go home. So the last thing to do is come up here, go to File, Fabrication Outputs, right? No, Plot. Come down to Plot. We're not going to be using solder paste, but we want our silk, our coppers, and our mask, and our cuts. And then these are pretty not very important. Here, we need to choose a folder though. So let's do new folder. Gerber. Open that. Yes. use Gerber, and at this point we pretty much can just click plot. So I'm gonna go ahead and close that, and then I'm gonna CD to that directory, CD documents, KiCad, RealRobot, what is it? Gerber. Alright, now I have all our Gerber files. We need to zip them up. So I'm going to zip. Actually, I'm going to read how to use zip real quick. Open the man page. So I need to do, I don't need to do zip minus R, do I? Use zip minus R. Actually, yeah, I can do zip minus R foo.zip foo. And go up one. Hey, there we go. Okay, so zip minus R Gerber.zip Gerber. And now I have all our Gerber zips, so that's time to go to JLC. Up here. And let's go to instant quote.
Oh yeah, you're changing this into Gerber. Is it Gerber or Gerber?
Gerber.
Gerber, the baby food.
Yeah.
And then you're sticking.
And then where is it? KiCad. There we go. RealRobot Gerber.zip.
So I did this way too much. Because I kept checking on the website.
Mm-hmm.
Making sure that they could. I didn't know there was a 3D keycap.
Yeah, it's pretty cool. So there you go. It's going to cost us $8.
Wow, that's pretty good.
Well, actually, we're gonna go ahead and make sure we pick our right. There you go. So that's actually, you know, I forgot something.
Seriously?
Yep.
When I was building a board, it was about that size, and it was like on like, I forgot the
Osh Park.
yeah, Ashmark.
Yeah, they're expensive for bigger boards.
Yeah.
They're really cheap for small things. But yep, there you go. You want to buy it, you can go buy it. I'm gonna put that up on GitHub. So if you want it to really look good, you want to buy INIG though. So that's another $15.8. Otherwise, it'll be silver instead of gold. Your logo, and gold's just better.
PCBs are so cheap.
Mm-hmm. Unless you get them in America. One thing about JLC is if you put JLC, no, they're Chinese.
Oh, okay, yeah.
If you put JLC somewhere, they'll put their order number there so you can hide it. I'm actually gonna do that because if we want this, we don't want JLC everywhere. JLC.
So they'll do what?
So I'm gonna put this right here. So I'm putting the order number for the PCB manufacturer under that, and I'm gonna go ahead and replot it.
And so what does that do for them? Is that just helpful for them?
You can tell them where to put the order number so you can hide it behind a chip and it won't be visible.
So they have to put the order number somewhere.
Yeah.
You can tell them to put it somewhere that it doesn't
Mm-hmm.
look bad.
Yep, basically. Instant quote. Add Gerbers. Add Gerber file. Gerber dot. No, that's not what I wanted. There we go.
Under the pick. So when you saw the pick, you can't see the order number.
Yeah.
Because they have to put the order number somewhere on the board.
Unless you pay him to not have an order number. But no one wants to do that. Yep, so different design one. Pins calculator, we chose JLC 2313. Let's get the top layer, F copper, inner one. These don't really matter. Inner one, inner two, and then bottom copper. So it tells them what copper layers. Sadly, apparently we can't get black. Darn. We want INIG, then specify location, it'll pull it up. JLC. Oops, I put it on the back, so it'll be visible. Dang it. Whatever, it doesn't matter. That takes 2 seconds to change. Let's do it again. Actually, I put that text on the back copper. That was retarded. I am skilled. Give me a job, please.
So is that something like
processing Gerbers. While that's going on, go get this correct. I get to do this again. Front copper, inner 1, into back copper. Purple would be great, but no. Definitely want to get gold and specify location. There we go. It's finally right. And I think we're done.
I think so.
That's how you make PCB from scratch. Thank you for coming.
Yes,